Let us talk about transaction and recovery. Database in database management system, transaction and recovery plays a very important role. And in this lecture, we need to talk about transaction, recovery, how a system and media can fail and recover, concurrency controller, and some more information we talk about. So first of all, let us talk about a transaction. A transaction is nothing but a set of action, a series of action that carried out by a single user or an application program which reads or updates contents of a database. But you understand that you are talking about a set of operations which are protected internally to help the ensuring the success of the operations. So transaction, when we look at it very clearly, a transaction is a logical unit of work on a database. Each transaction does something in the database, and no part of it alone achieve anything of use or interest. Transactions are Transactions are the unit of recovery, consistency and integrity as well. And the most important properties of transaction is ACID. What is that ACID properties? ACID properties talks about atomicity. That means every transaction is atomic. It is executed independently. Consistency. That means all the transactions are consistent. It never gets any inconsistent operation. Isolation. Every transaction is separated from each other, so there is isolation, and the transaction operation is either successful or failure, so it is highly durable. You remember one thing, that ACID properties are very important properties of transaction. Talking about all these 4 points, atomicity and consistency, you can see atomicity. Transactions are atomic, they don't have parts. Conceptually, can be executed partially, it should not be detectable, any interleave with another transaction. That means every transaction runs on its own. Consistency, transactions take the database from the consistent state into another, and in the middle of the transaction, the database might not be consistent. Why? Because there is something operation going on, operation is not complete yet. So atomicity, consistency, and look at isolation and durability. Isolation, the effects of transaction are not visible to other transactions. That means there are many transactions going on. Imagine Daj Bangla ATM used by so many customers from so many different points of the country, but their operations are all isolated from each other. From outside, the transaction has never happened, and to me, that actually sounds like a consequence of atomicity. Durability, once a transaction has completed, its changes are made permanent. That means you cannot change back. Even if the system crashes, the effect of the transaction must remain in place. Alright, so example of transaction, you can see you are transferring a fund from one account to the another. What you do? You read A first. Then, since you are transferring £50, so you subtract 50 from A, and then you write the new value of A, and then since you are transferring to B, so read B now and add 50 with B and then write B. So what you see, atomicity should not take money from A without giving it to B. That is atomicity. That means you have to ensure that A is subtracted first before giving it to B. Now, consistency is money is not lost or gained. Money is there, maybe one account from the other. And isolation, what could have lost if the consistency is lost? First, for example, it may happen that £50 is subtracted from A, but B did not receive, so it is not consistent. Isolation, every other queries should see that A and B change until completion. And durability, the money does not go back to A again. Yeah. So it's very clear about atomicity, consistency, isolation, and durability from this example. So if you are given a case, a set of transactions, you may have to identify that which one is atomicity, which one is consistency, which one is isolation, and which one is durability. All right. So the transaction manager is a very important person in the database. The transaction manager enforces the ACID properties. And It schedules the operation of transactions in such a way that it maintains the ACID properties. Commit and rollback are used to ensure atomicity. Atomicity is ensured by commit, means either you complete, or rollback means don't complete. Logs or timestamps are used to ensure the consistency of isolation, and a log is kept, which is the most important. Please remember, log is kept to ensure durability. Commit and rollback, you see, these two are very powerful statements in database. Commit signals the successful end of a transaction. That means when you say commit, it is done. It is highly durable. Any changes made by the transaction should be saved, and these changes are now visible to other transactions once it is committed. Rollback, on the other hand, signals the unsuccessful end of transaction. Any change made by the transaction should be undone, and it is now as if the transaction never existed. So commit and rollback is a very clear understanding. Now coming into recovery, how it happens, recovery transaction should be durable, but we cannot prevent all sort of failures. Sometimes system crash, power failure, disk crash, user mistake, sabotage, natural disaster. So recovery is a very important option that transaction control and recovery provides. Prevention is better than cure, we know. So most important is a reliable OS, operating system, security, UPS and surge protectors, RAID arrays, but cannot protect against everything though. So recovery is a very important option to think, and the recovery takes place through transaction log. Transaction log actually records the detail of each transaction. Any changes the transaction makes it to the database, how to undone these changes, and when transaction complete and how. The log is stored on the disk, not in the memory. Of course, it is a physical file, and if the system crashes, it is preserved. And write ahead log rule, the entry in the log must be made before commit process can complete. Okay. So system failure happens. System failure means all running transactions are affected, software crash, power failure, and the physical media are not damaged, of course. And at various times, DBMS takes a checkpoint. For example, all committed transactions are written to disk, and a record is made, of all transactions. So this is very important, the system failure aspects. Types of transaction, you can see here that there is a transaction. There are, how many transactions you can see? You can see 5 transactions are happening concurrently. T1 started earlier than T2. T2 started later than T3. And T4 and T5. So last checkpoint is one of the checkpoint is writing actually. At certain checkpoint you see that this transaction 1 is complete and the other 2 transaction is on, and system fails when the other 2 transaction was still running. So in that case, system recovery, any transaction that was running at the time of failure needs to be undone and restarted. That means you can see here in the previous diagram, we have actually 2 transactions who are running. One is T3, another is T5. Must be undone because the system failed that time. Any transaction that committed since the last checkpoint need to be redone. So one thing is restarted and redone. Transaction of type T1, you see, need no recovery. Why? T1 is already finished. And then transaction of type T3 and T5 need to be undone and restarted. See, T3 and T5 need to be undone and restarted. And transaction of type T2 and T4, you can understand this to be redone, right? Because these were running and we have no choice other than doing it again. So transaction recovery, undo and redo list of transactions, undo all transactions running at the last checkpoint, redo empty. So if the entry in the log starting at the last checkpoint, then if a beginning transaction entry is found, add T to undo, because that's actually logically you can decide whether you undo or whether you redo. And transaction recovery happens like this. You see here, this is a very important diagram because we will have actually our final exam and based on this transaction recovery points. And this diagram talking about checkpoint and failure, and you see which one is undo, which one is redo. That should be very, very clear. So last checkpoint and active transaction T233, you really have to redo again because we had other transactions may have some dependency on the data. So transaction recovery happens like this, this particular time we do undo T2, T3 and T4. You can see T2, T3 and T4 failure happened, but in between the checkpoint and failure, whatever transactions we had, which ones did not complete, T4 begins, you see, and add T4 to undo because T4 need to start again, yeah. So it's very clear. And transaction recovery, again you can say undo, what you do, T2, T3, T4 and T5, the checkpoint has moved. You can say I'm moving the checkpoints at different locations. You can see here, yeah. So checkpoints move from one end to the other end, yeah. You can see checkpoint I'm moving closer and then further closer and then further closer. So there is a changes in this particular diagram. Take a look at it very carefully again. This was the checkpoint before T4 and T5. At this time we do this, and then coming into checkpoint just immediate before T4 we do this. That means we are actually having a different scenario. Checkpoint having before T4 and T5, you see. So what happens, we need to have T2, T3, T4, T5. These are all between the checkpoints, you see. The checkpoint is the dotted line. So you understand that if and the failure happened, but we don't know about uncertainty about the transaction. So T5 begin and add T5 to undo because T5 need to, and undo also T2, T3, T4. So transaction recovery takes place based on the log, but it records all transaction states in terms of undo, redo, and commits from a point of view. So this is also another scenario of the checkpoint is different now. Undo T3, T5, you can understand T2, T3 and T5, T3 and T5, you can understand clearly that these two, while the T4 is already commits, so T4 is finished already. Look at the solid line, and the failure happened. Before failure, we had T3 and T5 was running. So look at the failure point, you can understand that which one need to undo and which one need to redo. So T2, T4 need to redo, but T5, T4, T4 is already commit here. Huh? Move T4 to redo. So redo has become, that means undo and redo we know, but T1 is already completed before the checkpoint, so there is no question. Now what happens forward and backward recovery? For backward recovery we need to undo some transactions, and working backward through the log we undo any operation by transaction on the undo list. The returns actually the database in the consistent state, and forward recovery some transactions need to be redone. Remember, backward means undo, forward means redo. So some transactions need to be redone, and working forward through the log we redo any operation, and this brings the database up to date. Yeah, okay. So media failure issues are there because media failure is too expensive, too difficult, but we still use the RAID and other architecture to overcome this. So these are the kind of backups are needed to recover from the media failure. Backup is very important, and we do incremental backups. We try to take backups on a regular basis, and we try to record them. So recovery from the media failure happens, restore the database from the last backup generally, and use the transaction log to redo any changes made during the last backup. If the transaction log is damaged, you cannot do step 2, so no choice. And in that case, store the log on a separate record. The best, you have to have a log, otherwise difficult. Concurrency happens as because large databases are used by many people. There are so many transactions happens at the same time, and it is very important that we make sure that every transaction is safe and done consistently. If we do not allow concurrency, then transactions are run sequentially. But concurrency, you have no other choice because you have to allow the problem. But what is the problem? In order to run transaction concurrently, we interleave their operation, and every transaction gets a share of the computing time. This leads to several sort of problems. What? Lost updates, uncommitted updates, incorrect analysis. So concurrency has a big problem to solve, and always isolation is broken. So last update, I just want to talk about this last update. For example, there are two transactions. This is very important diagram. Please take note. We have two transactions, transaction T1 and T2. In T1, we are reading X and then subtracting X, 5 from X. While I'm subtracting, I still did not write, see, I still did not write X, but I'm reading X. That means I'm getting in transaction 2 a dirty value of X, right? And then I'm adding 5. I write X and write X is two different X. So what happens in T1, T2 read X, both modify it, then both write it. So the net effect of T1, T2 should be no change on X, but T2 changes is, however, the value of X increased by 5, but it is a dirty read type of. So uncommitted updates you see here. T1 you're reading and then you actually write, you subtract and you write, it's fine. T2 you read, you update and you write. When you say T1 rollback, you go back to the previous value, but unfortunately T2 has committed. So what happens? Uncommitted update. Uncommitted update. You see, rollback is uncommitted, but you have updated. So T2 sees the change to X made by T1, yes, of course, but T1 is rollback. So the change made by T1 is undone, right, because it is rollback, and it should be as if that change never happened. Inconsistent analysis, you see the scenario. Here we have two transactions, T1 and T2. T1 I'm reading X, subtracting and writing, it's fine. I still did not commit, please remember. And then T2 I'm reading X, read Y, another different value, and sum is equal to X plus Y. But when I'm read Y and sum is equal to X plus Y, I read Y also in T1, add 5 and write 5. T1 does not change the sum of X plus Y, of course not. But T2 sees a change. Why? Because you already wrote it. So T1 and T2, T1 does not change the sum of X plus Y, but T2 sees a change. T1 consists of two parts. Take 5 from and then add 5 to Y. And T2 sees the effect of the first but not the second, because Y did not change. While actually you read Y in T2, you did later change in Y. So it's inconsistent analysis. Alright, so I think we are done on this part of the discussion, and I hope you remember, review all these transaction and recovery slides very, very carefully, because we are going to actually have a final exam understanding on this. This part is very, very important to all of us. So appreciate again your time and your patience and enjoy the database, which is very, very important.